So good day. Today we're going to make the 4-bit adder and the 4-bit subtractor. So as you can see in this truth table, we have two inputs of A and B and an output of S and C. S indicates the sum and C is for the carry. So as you can see here in S, it has an output of 0, 1, 1, 0, and that can be interpreted as the XOR combination of A and B. And for the C, it only had one output if both of the input is 1, 1. So we can have the A and B, unended A and B. So here we now going to make. So this truth table is for the half adder. So in logism, so this, we need to have a case of OR, XOR, and 2. We have two inputs, A and B. Indicate A, and this is B. So this is for the sum, the S, and this is for the C, carry. We have this output, first output for the sum and output for the carry. So as we can see in this table, if 0 plus 0, the sum must be also 0. So 0. And the carry must also be 0. But if we add 1, 0, say 1, 0, the sum is 1. And the carry is 0. But if we add both 1 and 1, the sum is 0 and the carry is 1. So this can be, this circuit is the half adder. So to construct a full adder, we only need to combine two half adder. So the only difference between the half adder and the full adder is that it has a third input, and that input is for the carry. This here, we can call it the C-in. C-in. So with C-in, we need to duplicate the half adder. So the sum is connected to the both inputs of for the carry and the sum, and then for the C-in, so the carry must be must OR together, so they can be added. So gates, the OR gate for the OR gate, and the sum must now be here. Put so we undid both the carry. So now we need to test it. So 1 plus 1 in binary 1 plus 1 is 2, so the carry must be 1. And then if we try to have a carry in this 1 plus 1, we can expect that the sum must be 1 and the carry is also be 1. So we can call this as the full adder. So we're going to make the 4-bit adder. So when constructing this, we need to have a combination of half and full adders. So we need to make the input first. So since this is 4-bit, we need to have 4 bits. So we have 2 inputs, right? And then for the first bit, we only need to have a half adder. Since we cannot expect another carry at the first at the rightmost bit. Why? Because there's no existing bits from the right of it. So the carry will not exist here. So we only need to connect it to the half adder. So for the next, we need to connect it now to the full adder since there is a carry now. Like if we add 1 plus 1, there is a carry of 0, of 1. So we need to have a full adder. We need to have 3. So this is for the input, right? So this is for the carry. Okay, carry. We connect that carry to the Cin. Carry. Cin. Carry. C. So this is for the input A. This is for the B. And that is for the B. So by having this, we need to connect it now. So this is for the input. This is for the input B. And this is for the A. Okay. And input B. B. A. A. Input B. We can have now the outputs. So for the output, we're going to make a 5 bits. Since we can expect some carry if we try to add binary. So there is also always an excess of 1 bit so that it can indicate if there is an carry. So this is for the output. For the first bit, bit, third bit, fourth bit, and this will indicate the carry if there is a carry. So if we try, so 1 plus 1, so 0, 1 plus 0, 1, it, it will have a 2. So, and then if we try to add, let's say 9 plus 9, since the leftmost is 1, we can expect a carry here. So 1 plus 1 should be carry 1. So the sum is 0 and the carry is 1. So that's this is a functional 4-bit adder. But we can also use make a 4-bit adder by only using this. So this is the adder, right? So we need to have an input. If we try to make a 4-bit, we need to change the data bits into 4. So this also be changed to the 4-bit. So we connect it. This is the input. And this will indicate the output. Output also be in 4-bit. And then the C out, we can just use this. It will indicate the carry if there's an existing carry. So like here, so we need to do this also. So 9 plus 9, so 1, 1. See, it is the same answer. So there's a carry of 1. And then the sum is 0, 0, 1, 0. Okay, so moving on, we're going to make now uh, the 4-bit subtractor. It's just the same process. So we make the half subtractor, the full, and then we make the 4-bit sub. For the half subtractor, we need to look at this truth table. So in this truth table, the difference is the output for the difference is just the XOR of a B. And if we look at the borrow for the B, the borrow, if we differentiate 0 minus 1, the difference is 1, and there is a borrow for the next bit of 1. So for the formula for this borrow is A complement B. So we need to have a gates of XOR and then a AND. So as we can see here, TA is complemented. So we need to have a NOT gate. So two inputs again, A and B. And for the A, we need to connect it to the NOT gate and AND, and then ANDed by another input. So we have this output. We can name it as for the difference, and this is for the borrow. So test it. 1 minus 1. If we had 1 minus 1, we can have, we will then have the difference of 0 and the borrow of 0. If we try to have 0 minus 1, the output must be also 1. And there is a borrowing of 1 for the next bit. So after we did the half subtractor, we need to then now make the full subtractor. For the full subtractor, it's just a combination of two half subtractors. So we here. So and then we add another input for the borrow. Duplicate this. So this is for the input for the borrow input. Okay. So for the difference, this, this difference must also be the borrow must also be ORed to one another. So we need to have a gate of OR gate. We need to OR it, and this is for the difference. Okay. Difference, and this is for the borrow. Let's say we're going to subtract 1 minus 1. So we can expect that the difference must be 0. And if we try to make 0 minus 1, both the difference and borrow must light up 1 and 0, right? And then and now we're going to make the 4-bit subtract. So that is just same in the 4-bit adder, same concept, but the only difference is uh, the ICs that were used that in so we only need to change the ICs. So the first bit we only need to have the uh, hub subtractor, full subtractor in the last. So by testing it, so we need to have this. So for let's say we need to subtract 4 minus 1. 4 minus 1. So we have the answer of 3. Also 1 plus 2 is equals to 3. So let's say we have 9 minus 1. We have the 8. Say 9 minus 1, we have the 8. Right? Now, what if the first bit is greater than, is less than the second 4-bit? Let's say we have here let's say 4. 1 minus 4. So it is negative 3, right? So if our answer is negative, the borrow must be 1. There is also a 1. There must be a 1 here, and that indicates that our answer must be is a negative number. So let's say here 1 minus 4. So 1101. That is our answer. And if we try to check it, we need to find the ones complement of this. So let's say 0010. That's the inverted. And then if we try to add 1, if we need to, if we're going to find the second complement, second 2s complement, we can have the answer of 3. So this indicates that it is negative. So our answer must be -3. So another simplest way to do this in logism is by having this arithmetic IC, the subtractor. Okay. So we need to have the 4-bit. Okay. Here's the 4-bit. Output. Then the borrow. As a like this. So 1 minus 4. 1 minus 4. Just the same here, right? So that's it. Thank you.